Hello. Today we will discuss the 17th largest solar flare that occurred in May 2024. This event has sparked great excitement in the field of space science and solar physics. We will provide detailed information about the new solar flare and explain what solar flares are and how they work. If you're ready, let's get started. Solar flares are sudden bursts of energy on the surface of the sun. These flares can last from seconds to minutes and release a significant amount of energy. But where does this energy come from? Solar flares are caused by sudden changes in the sun's magnetic fields. The magnetic field lines on the sun's surface constantly interact with each other and sometimes rearrange. During this rearrangement, a large amount of energy is released. Solar flares emit energy across a broad spectrum of electromagnetic waves, but they mainly appear as X-rays and radio waves. This energy concentrates in the sun's outer atmosphere, called the corona, heating the plasma to millions of degrees. One of the fascinating aspects of this event is that the energy bursts can travel vast distances in space, not just staying confined to the sun's surface. When these energy waves reach Earth, they create various effects. The amount of energy emitted by a solar flare can be equivalent to billions of megatons of TNT, about 1 billion times more powerful than the atomic bomb dropped on Hiroshima. Solar flares create space weather, which interacts with Earth's magnetic field and atmosphere, leading to various phenomena. Solar flares are classified based on their strength into 5 main categories: A, B, C, M, and X. Each category is 10 times stronger than the previous one, with X-class flares being the most powerful, releasing massive amounts of energy. An X20 classification indicates an X-class flare's strength. For instance, an X20 flare is 20 times more powerful than an X1 flare. A-class flares are the weakest and typically have no noticeable effect on Earth systems. B and C-class flares are slightly stronger and may cause minor radio communication interruptions. M-class flares are moderately powerful and can often cause auroras in polar regions. X-class flares are the most powerful and can have serious global effects, such as significant radio communication disruptions, GPS errors, and even problems in electrical grids. Solar flares are continuously monitored by various observatories and space telescopes around the world. These observations are crucial for understanding the sun's dynamics and predicting such events. Observatories record the start, peak, and end of the flares, providing valuable data to understand how and why solar flares occur. The primary instruments used to observe solar flares include NASA's Solar Dynamics Observatory, the European Space Agency's Solar and Heliospheric Observatory, and Japan's Hinode spacecraft. These instruments can capture high-resolution images of the sun's magnetic fields, surface features, and the energy of the flares. Observing solar flares is not limited to technological instruments alone. Amateur astronomers can also observe solar flares, though it is essential to use special solar filters to avoid severe eye damage. Telescopes used for solar observation allow detailed examination of sunspots and flares, providing important data to understand the sun's dynamic structure and monitor the development of flares. In May 2024, a particularly large and impressive flare occurred on our sun. This flare was recorded as the 17th largest solar flare in history. This event happened during an active period of the sun, exciting and surprising scientists. The energy from the flare affected many devices and systems on Earth. This flare was one of the peak points of solar activity in 2024. Within the sun's 11-year cycle, there are increases and decreases in the number of sunspots and flares. The peak periods of these cycles are when the sun is most active, and large flares are more common. The 2024 flare was closely followed as part of this cycle. This significant flare resulted from a sudden rearrangement of a massive magnetic field on the sun's surface. The sun's magnetic fields continuously become complex due to surface movements, accumulating energy. When this energy exceeds a certain threshold, it is suddenly released, leading to a large flare. The source of the flare was a massive magnetic field knot in an active region of the sun. This region is associated with sunspots, which form when strong magnetic fields rise to the surface. In sunspot regions, magnetic field lines concentrate, sometimes leading to large energy bursts. During this flare, a large amount of energy was ejected from the sun's surface, traveling towards Earth. These energy waves move with plasma streams known as the solar wind. The solar wind is a flow of charged particles continuously emitted from the sun. During a flare, this wind intensifies and interacts with Earth's magnetosphere, causing magnetic storms. This large flare had various effects on Earth. Communication and GPS systems were particularly affected, causing short-term disruptions. Additionally, auroras were exceptionally bright and widespread in the northern and southern hemispheres. The effects of this flare were not limited to technological systems. Changes in the atmosphere also impacted air traffic. Flights in polar regions had to alter their routes due to high radiation levels. Such events pose significant risks to the aviation sector, and solar activities are continuously monitored for this reason. The large solar flare in May 2024 was observed by solar observatories and space telescopes worldwide. Observations clearly recorded the start, peak, and end of the flare. Such data is extremely valuable for understanding the dynamics of solar flares. Scientists use data obtained during such flares to better understand how and why solar flares occur. Additionally, efforts are made to predict and mitigate the effects of such events on Earth. Solar flares can particularly affect high-frequency radio communications. During such flares, the free electron density in the ionosphere increases, making it difficult for radio waves to propagate. This situation can cause disruptions, especially in shortwave radio communications. Critical radio communication services such as air traffic control, maritime and military communication systems can be affected by such flares. Disruptions in radio communications can create significant problems, especially during emergencies. Reliable radio communication is crucial during natural disasters or military operations. Disruptions experienced during solar flares can pose serious risks in such situations. Therefore, making radio communication systems resistant to solar flares and developing alternative communication methods is important. GPS systems rely on signal propagation in the ionosphere for accurate positioning. Solar flares can disrupt these signals, causing GPS positioning errors. These errors can create problems, particularly in high-precision military and civilian applications. For example, GPS-based systems in air traffic management, maritime, and agriculture sectors can be affected by solar flares. GPS errors can also cause various problems in daily life. Smartphones, navigation devices, and in-car systems provide location information based on GPS signals. Signal disruptions during solar flares can cause these devices to give incorrect location information and mislead users. Such errors can lead to serious accidents, especially in densely trafficked areas and on dangerous roads. Solar flares can interact with Earth's magnetic field, causing induced currents in power grids. This situation can cause voltage fluctuations and even power outages, especially in high-latitude power grids. Such events can threaten the security of the power infrastructure and lead to significant economic losses. An example of such effects is the solar flare that occurred in Quebec in 1989. During the event, a widespread power outage occurred in Quebec, Canada, leaving millions of people without electricity for hours. This event demonstrates the potential impacts of solar flares on power infrastructure. Making power grids resistant to such events and developing emergency plans is important to prevent similar problems in the future. High-energy particles emitted by solar flares can damage the electronic components of satellites. Such events can cause temporary or permanent malfunctions in satellites. Communication, navigation, and observation satellites can be affected by solar flares. This situation can disrupt satellite-based services and cause data loss. Various measures are taken to protect satellites. For example, satellites' electronic components are made resistant to solar flares, and sensitive devices can be turned off during such events. Additionally, satellite operators can monitor solar flares and take necessary precautions during such events. Protecting satellites is critical to ensuring the continuous operation of space-based services. Solar flares can cause large energy discharges in Earth's magnetosphere, leading to the formation of auroras. Auroras are usually seen in polar regions, but during large solar flares, they can also be seen at lower latitudes. Such events create magnificent light displays in the sky, and are a great interest for both scientists and amateur observers. Auroras form as charged particles interact with Earth's magnetic field. These particles collide with gas molecules in the atmosphere, emitting light. This light is typically seen in green and red colors, but sometimes blue and purple colors can also be observed. Auroras are visually impressive and provide important clues for observing the effects of solar flares on Earth. One of the most famous and impactful solar flares is the Carrington event that occurred in 1859. This flare is named after the solar observer, Richard Carrington, who observed it. The Carrington event is known as the most powerful solar flare recorded in history and caused widespread magnetic storms globally. During this event, telecommunication lines were damaged and widespread power outages occurred. Additionally, extraordinarily bright auroras were observed in the northern and southern hemispheres. The Carrington event serves as an important example of the potential impacts on modern society. Since technological infrastructure was relatively simple at that time, the effects were limited. However, a similar event today could have much more widespread and destructive consequences. In 1989, a large solar flare caused a widespread power outage in Quebec, Canada. This event caused the collapse of the power grid in Quebec within minutes, leaving millions of people without electricity for hours. This flare serves as an important example of the potential impacts of solar flares on power infrastructure. The Quebec event has been an important lesson in understanding the impacts of solar flares on power grids and taking protective measures against such events. After the event, power companies and governments have taken various measures to make power grids resistant to solar flares. These measures include using voltage regulators in power grids, backing up critical systems, and developing emergency plans. The series of powerful solar flares that occurred in October and November 2003 is known as the Halloween storms. These flares caused disruptions in many communication and navigation systems worldwide. Additionally, the effects on satellites and space vehicles were significant. These events once again highlighted the impacts of solar flares on Earth's technological systems. The Halloween storms have been an important turning point in understanding the impacts of solar flares on technological systems and being prepared for such events. During these events, major disruptions were experienced in radio communication, GPS systems, and satellite-based services. Such effects have demonstrated how sensitive modern society is to solar flares. In May 1921, a major solar storm caused significant impacts worldwide. This event is also known as the New York Railroad Storm. During the solar storm, magnetic storms occurred globally, damaging many telecommunication lines. Additionally, significant damage occurred in electricity and telegraph lines. The 1921 solar storm is one of the largest solar storms that occurred before the modern era and created similar impacts to the Carrington event. This event once again highlighted the potential impacts of solar flares on technological systems and daily life. After the event, various studies were conducted to understand the effects of magnetic storms and develop protection methods against such events. In August 1972, a major solar flare caused significant impacts worldwide. This event particularly affected military and communication systems. During the flare, the U.S. Navy's submarine communication systems experienced major disruptions, causing serious problems in military operations. The 1972 solar flare is an important example of the potential impacts of solar flares on military and communication systems. After the event, various measures were taken to make military and communication systems resistant to solar flares. These measures include backing up critical systems, protecting sensitive devices, and developing emergency plans. In February 1960, a major solar flare caused significant impacts worldwide. This flare particularly caused major disruptions in radio communication systems. During the flare, significant disruptions were experienced in shortwave radio communication globally, causing serious problems in communication systems. The 1960 solar flare is an important example of the potential impacts of solar flares on radio communication systems. After the event, various measures were taken to make radio communication systems resistant to solar flares. These measures include protecting sensitive devices, developing alternative communication methods, and creating emergency plans. In March 1851, a major solar storm caused significant impacts worldwide. This event caused significant damage to telecommunication lines and rendered many telegraph lines inoperative. Additionally, exceptionally bright and widespread auroras were observed. The 1851 solar storm is an important historical example to understand the potential impacts of solar flares on technological systems and daily life. After the event, various studies were conducted to understand the effects of magnetic storms and develop protection methods against such events. Such events are an important reminder of the power and potential impacts of solar flares. Scientists conduct intensive research to understand the dynamics of solar flares. Understanding how the sun's magnetic fields form, change, and lead to solar flares is a primary goal of these studies. The dynamics of solar flares are studied using computer simulations and observational data. The sun's internal structure and the dynamics of its magnetic fields are critical to understanding how flares occur. The sun's magnetic fields are constantly reshaped by plasma movements on the sun's surface. This process can lead to large amounts of energy accumulation and sudden release of this energy. Scientists are working to understand how these flares develop by monitoring and modeling the sun's magnetic fields. The primary instruments used to observe solar flares include NASA's Solar Dynamics Observatory, the European Space Agency's Solar and Heliospheric Observatory, and Japan's Hinode spacecraft. These instruments can capture high-resolution images of the sun's magnetic fields, surface features, and the energy of the flares. SDO continuously monitors the sun's magnetic fields and surface movements. These observations provide critical data to understand how and why solar flares occur. SOHO is used to observe the sun's corona, studying the impacts of flares in space. Hinode provides high-resolution images of the sun's magnetic fields, helping to understand the dynamics of flares. These instruments are also used to predict and minimize the impacts of solar flares on Earth. Observational data help create models to predict the timing and intensity of solar flares. These models are crucial for understanding the potential impacts of solar flares and taking preventive measures. Another method used to understand the dynamics of solar flares is theoretical models and computer simulations. These models are used to understand how the sun's magnetic fields form, change, and lead to solar flares. Computer simulations provide detailed examination and comparison of these dynamics with observational data. Theoretical models are used to understand the complex structure of the sun's magnetic fields and how they change. These models simulate plasma movements in the sun's interior and how magnetic fields are reshaped. Computer simulations are used to test the accuracy of these models and understand the dynamics of solar flares better. To minimize the future impacts of solar flares, scientists and engineers are developing various protective measures. Especially for communication, energy, and satellite systems, various precautions are taken to prevent them from being affected by solar flares. These precautions include backing up critical systems, turning off sensitive devices during solar flares, and using voltage regulators in power grids. These precautions are critical to minimizing the impacts of solar flares on technological systems. For example, voltage regulators used in power grids minimize the effects of induced currents during solar flares. Additionally, satellite operators can monitor solar flares and turn off sensitive devices during such events, ensuring the continuous operation of satellite-based services. One of the most effective ways to reduce the impacts of solar flares is early warning systems. These systems detect solar flares in advance and provide timely information to relevant organizations and the public. NASA and other space agencies use various satellites and telescopes to monitor and predict solar flares. These systems ensure that solar flares are detected before they reach Earth, allowing necessary precautions to be taken. Early warning systems are critical to minimizing the potential impacts of solar flares. These systems predict the timing and intensity of solar flares, allowing relevant organizations and the public to take necessary measures. These systems play an important role in protecting critical systems such as radio communication, GPS services, and power grids. Raising awareness and educating the public about the potential impacts of solar flares is also extremely important. Efforts in this area ensure that the public is informed about solar flares and their effects. Educational programs are important to prepare professionals working in the technology and energy sectors for such events. Awareness and educational programs provide information about the potential impacts of solar flares and help to be prepared for such events. These programs can be organized in schools, universities, and workplaces. Additionally, public awareness campaigns can be used to create awareness about the potential impacts of solar flares. Future research to better understand the dynamics and impacts of solar flares is extremely important. Scientists continue their studies to understand how the sun's magnetic fields form, change, and lead to solar flares. Additionally, new methods are being developed to predict and minimize the impacts of such events on Earth. Future research areas include better understanding the sun's magnetic fields, better modeling the dynamics of solar flares, and better predicting the impacts of solar flares on Earth. Such research is critical to minimizing the potential impacts of solar flares and protecting technological systems. The large solar flare that occurred in May 2024 is considered a major step in solar physics and space science. Such events help us understand the dynamic and ever-changing nature of the sun. At the same time, they are important to understand the potential impacts of these flares on Earth and be prepared for them. Solar flares will continue to affect us in the future. Scientists continue to work to understand and predict such events better. The sun's magnetic cycles reach their peak every 11 years, and the likelihood of large solar flares increases during these peak periods. These cycles are a result of the magnetic activity occurring on the sun's surface and are characterized by an increase in the number of sunspots. Future large solar flares can have serious impacts on our technological systems. For example, a major solar storm that narrowly missed Earth in 2012 could have caused significant damage to modern technology if it had directly hit our planet. This event was of the same magnitude as the Carrington event and could have caused widespread disruptions in power grids, satellite communication, and GPS systems if it had struck Earth. New methods are being developed to protect and minimize the impacts of such events on our technological systems. For example, protective devices and systems used in power grids can detect and block induced currents during solar flares. Additionally, satellite operators use special coatings and electronic circuits to make satellite hardware more resilient. Early warning systems play a crucial role in reducing the impacts of solar flares. These systems detect solar flares in advance and provide timely information to relevant organizations and the public. Thanks to such warnings, power companies and satellite operators can take necessary precautions. For example, when a strong solar flare is detected, power companies can make voltage adjustments in their grids, and satellite operators can turn off sensitive devices. Raising awareness and educating the public about the potential impacts of solar flares is also extremely important. Efforts in this area ensure that the public is informed about solar flares and their effects. Educational programs are especially important to prepare professionals working in the technology and energy sectors for such events. Social preparation is crucial to minimizing the impacts of solar flares. Raising public awareness, creating emergency plans, and regularly testing these plans ensure preparedness against the potential damage caused by solar flares. For example, in Japan, schools and workplaces regularly conduct disaster drills aimed at preparing for unexpected events like solar flares. In the future, research to better understand the dynamics and impacts of solar flares will continue. This research will focus on better understanding the sun's magnetic fields, better modeling the dynamics of solar flares, and better predicting the impacts of solar flares on Earth. For example, NASA's Parker Solar Probe mission aims to closely examine the sun's outer atmosphere the corona, to help us understand how solar flares begin and spread. Scientists are developing new methods to predict and minimize the impacts of solar flares on Earth. For example, artificial intelligence and machine learning technologies can be used to predict solar flares. Such technologies can analyze large datasets and more accurately predict when and how powerful solar flares will be. The European Space Agency's Solar and Heliospheric Observatory has been an important tool for monitoring and understanding solar flares. Since 1995, SOHO has been observing the Sun's outer atmosphere and has detected many major solar flares. These observations provide critical data to understand the dynamics of solar flares. The Parker Solar Probe mission by NASA is designed to closely examine the Sun's outer atmosphere, the corona. This spacecraft makes closer passes to the Sun than any other spacecraft, collecting data that will help us understand how solar flares begin and spread. The Space Weather Prediction Center, SWPC, of the U.S. National Oceanic and Atmospheric Administration, NOAA, is an important center for monitoring and predicting solar flares. The SWPC detects solar flares and provides early warnings to relevant organizations and the public. Such warnings are crucial for minimizing the impacts of solar flares. The Sun is as much a source of life as it is a dynamic star we must continuously observe and understand. Every new discovery about it contributes to a broader understanding of the universe. Continue to follow this fascinating topic and uncover the secrets of the Sun. In our next video, we will cover another exciting space phenomenon. Until then, may the light of the Sun be with you.